Look at the National Hurricane Center forecast. The Atlantic Basin is entirely dormant. Not a single depression, storm, or hurricane exists on this map. Yet, a glance at the Southeast Regional Radar reveals a violent, deep red corridor of explosive convection. We are witnessing a paradox. A life-threatening, historic flooding emergency driven by a completely nameless atmospheric roadblock. Today, we are going to deconstruct the physics of the atmospheric freight train currently drowning the Gulf Coast, and examine exactly why federal hydrologists are warning that the most catastrophic phase of this event is still yet to come. To understand the sheer scale of the disaster unfolding across the Southeast, we first have to discard the traditional metrics of severe weather. The danger in this exact moment is not defined by rotational velocity, tornadic debris signatures, or the Saffir-Simpson scale. The apex predator of this particular meteorological setup is something far more insidious, governed by a phenomenon known to atmospheric scientists as echo training. When you look at standard weather radar, you are generally observing a transient event. A squall line forms, it sweeps across the map from west to east, it drops an intense but brief volume of precipitation, and it departs. The ground absorbs the moisture, the drainage systems process the runoff, and the equilibrium of the local hydrology is restored. What we are observing on the radar composite over the Gulf Coast today is fundamentally different. These storms are not moving laterally. Instead, they are undergoing a process of continuous, localized regeneration. The radar returns show distinct, violent thunderstorm cells developing, maturing, and precipitating over the exact same geographical coordinates, one after another, in a relentless sequence. In meteorological terms, these storms are training. Think of it as an atmospheric freight train. The track itself is entirely stationary, draped across the coastal plains of the Southeast. And just as a stationary track allows an endless procession of boxcars to roll over the exact same railroad tie, this stationary atmospheric boundary is guiding discrete, massive thunderstorm cells over the exact same saturated zip codes. Cell 1 arrives, drops 2 inches of rain, and dissipates. Cell 2 immediately forms behind it, follows the exact same vector, and drops another 2 inches. Cell 3 is already developing in its wake. There is no spatial progression. There is only temporal repetition. To truly grasp the catastrophic nature of this freight train effect, we must shift our perspective away from the macroscopic satellite imagery and look directly at the microenvironment below. We have to look at the concrete, modern municipal infrastructure, the asphalt arteries, the curb and gutter alignments, the subterranean network of catch basins and lateral storm pipes is an engineering marvel designed entirely around statistical probabilities. When civil engineers draft the blueprints for a coastal city's stormwater system, they design it to manage what is known as the design storm. In many Southeast municipalities, this infrastructure is built to flawlessly handle a severe, high-intensity, 30-minute downpour. The engineering math relies on a fundamental assumption that after the initial barrage of water, the storm will move on, granting the system the necessary time to gravity drain the accumulated volume into local outfalls, retention ponds, and coastal estuaries. Let us walk through the physics of what happens when that assumption fails under the weight of an atmospheric freight train, when Cell 1 of our training storm complex makes landfall over a suburban grid. The infrastructure performs exactly as designed. The torrential rainfall hits the impervious surfaces, roofs, driveways, 4-lane stroads. Because this water cannot penetrate the concrete, it becomes surface runoff. It races down the slight parabolic crown of the asphalt, guided by the concrete curbs into the steel grates of the catch basins. From there, it drops into the subterranean network of corrugated high-density polyethylene and reinforced concrete pipes. The pipes fill to perhaps 60% of their volumetric capacity. The hydraulic head, the pressure exerted by the elevation of the water, pushes the flow efficiently toward the local river outfall. The streets remain clear. The system is working. But then, 45 minutes later, Cell 2 arrives. The environment has fundamentally changed. The grassy medians and residential lawns, which previously absorbed a fraction of the rain, are now fully saturated. Their coefficient of runoff has shifted from a sponge to a sheet of glass. Now, 100% of the falling water is rushing directly into the storm grates. Beneath the street, the concrete trunk lines have not yet evacuated the water from Cell 1. As the runoff from Cell 2 plunges into the system, the pipes reach 100% capacity. They become surcharged. Water is an incompressible fluid. Once a closed subterranean pipe is completely full, it cannot accept another drop. But the atmospheric freight train does not care about subterranean fluid dynamics. Now, Cell 3 hits. Millions of gallons of water are crashing down onto the exact same square mile of pavement, seeking entry into a municipal grid that is already choking. The hydrostatic pressure inside the pipes rapidly equalizes with the surface. The catch basins, designed to vacuum water off the streets, suddenly reverse their function. The immense pressure of the trapped water forces it violently upward. The steel grates become geysers, spewing the subterranean runoff back onto the asphalt. This is the exact moment a localized weather event transitions into a structural disaster. The streets transform into open channel rivers. The hydraulic lock prevents any newly falling rain from draining, forcing the water level to rise vertically. It breaches the 6-inch concrete curbs. It overtops the sidewalks. It begins to press against the foundations of residential homes, seeking the path of least resistance through doorways, weep holes, and microscopic cracks in the masonry. As Cell 4, Cell 5, and Cell 6 continue to roll down the track, the municipal infrastructure is completely paralyzed. The concrete engineered to protect the city becomes a bathtub trapping the water inside. The vehicles parked on the street begin to experience the merciless reality of Archimedes' principle. As the displaced water weight equals the weight of the vehicle, 2-ton cars lose their frictional grip on the asphalt and become floating, destructive projectiles drifting blindly in the current. This is the silent, mechanical horror of the training storm. It does not destroy with a single spectacular blow of wind. It destroys through attrition. It breaks the mathematical assumptions of civil engineering, weaponizing the very infrastructure designed to mitigate it until the city drowns from the ground up. If the training thunderstorms are the boxcars on the freight train, we must step back and examine the macro-level engine that is laying the track. Why are these storms anchored in place? Why has the normal west-to-east progression of weather completely ceased across the southern United States? To answer this, we have to look thousands of feet above the flooded concrete into the mid-levels of the troposphere. In a typical meteorological environment, weather systems are strictly transient passengers. They are chauffeured across the continent by the upper-level steering currents, most notably the jet stream. These high-altitude rivers of air, located roughly 18,000 to 30,000 feet above sea level, are driven by the thermal contrast between the cold polar latitudes and the warm equatorial regions. When these temperature gradients are sharp, the jet stream is a tight, fast-moving ribbon that efficiently sweeps frontal boundaries and the rain they produce, from west to east. It acts as the atmosphere's ventilation system, ensuring no single region takes the brunt of a storm for too long. But currently, the atmosphere over the North American continent has achieved a state of catastrophic stagnation. When you analyze the 500 millibar charts for this week, you do not see a sleek, progressive jet stream. Instead, the upper-level flow has buckled into a massive, high-amplitude blocking pattern. The primary steering currents have meandered wildly far to the north, completely bypassing the southern United States. In the absence of these prevailing winds, an upper-level, low-pressure system has detached from the main flow. It has been effectively orphaned, left to spin aimlessly over the lower Mississippi River Valley. Without the jet stream to push it eastward, this system is idling in park. At the surface, this translates into a stalled frontal boundary. A cold front that was attempting to push south toward the Gulf of Mexico simply ran out of kinetic energy. The upper-level winds required to drive it forward vanished. As a result, this boundary has draped itself like a stationary scar across the Gulf Coast, stretching from eastern Texas through the Florida Panhandle and up into the Carolinas. This stationary boundary is the physical track of our freight train. It acts as a permanent wall of low-level convergence. When the warm maritime air blowing inland off the Gulf of Mexico hits this stationary front, the air is forced to rapidly ascend. This vertical forcing creates the thunderstorms. Because the front is not moving, the forcing mechanism never leaves. It operates exactly like a stuck conveyor belt. Imagine a massive industrial conveyor belt in a factory. Under normal conditions, the belt carries raw materials, in this case, moisture, drops them off at a station, and continues moving the finished product down the line. But our atmospheric conveyor belt has jammed its lateral gears. The engine is still running at maximum capacity, continuously pulling millions of tons of raw, saturated air off the surface of the Gulf of Mexico and hurling it upward into the atmosphere. The belt pulls, the air rises, the moisture condenses, and the rain falls. But because the lateral motion is entirely broken, the belt just keeps dumping its cargo in the exact same pile, over and over again, in an endless loop of vertical extraction and localized precipitation. The upper-level steering currents have abandoned the region, leaving behind a self-sustaining thermodynamic engine that is perfectly calibrated to pull moisture from the ocean and wring it out over the land, hour after hour, day after day. The stuck conveyor belt will not shut off until the entire hemispheric flow pattern reorganizes, a process that forecasting models indicate is still days away. Understanding the mechanical track in the stuck conveyor belt explains why the storms are standing still. But to understand the sheer explosive violence of the rainfall rates exceeding 3, 4, and sometimes 5 inches per hour, we have to examine the thermodynamic fuel powering this system. This flooding emergency is not an isolated variable. It is deeply, inextricably linked to the severe 112-degree heat advisories currently roasting the regions just outside the precipitation shield. We are dealing with a cascaded systemic failure where extreme heat acts as an atmospheric battery. Physics dictates the rules of this escalation through the Clausius-Clapeyron relation. This fundamental thermodynamic equation establishes that for every 1 degree Celsius increase in atmospheric temperature, the air's capacity to hold water vapor increases by roughly 7%. It is an exponential curve. Right now, the sea surface temperatures in the Gulf of Mexico are anomalously hot, running well above their historical averages for this time of year. Above this boiling bath of salt water sits a dome of oppressive, stagnant heat. The air is not just hot, it is possessing a terrifying amount of convective available potential energy, CAPE. This air mass has spent weeks acting like a sponge, absorbing an astronomical volume of evaporated seawater. Because of the extreme heat, the atmosphere's battery is charged to its absolute maximum capacity. It is holding an oceanic volume of water in a gaseous state. When this supercharged, boiling air mass is pulled northward by the stuck conveyor belt and collides with our stalled frontal boundary, the resulting reaction is highly violent. The air is violently forced upward into the cooler mid-levels of the troposphere. As it rises, it cools, and it hits its dew point. This is where the concept of latent heat release supercharges the disaster. When water vapor condenses from a gas back into a liquid raindrop, it releases latent heat into the surrounding air. This suddenly released heat warms the air inside the thunderstorm, making it more buoyant. The air rises even faster, creating an even more violent updraft, which in turn sucks up even more moisture from the Gulf, creating even more condensation, which releases even more heat. It is a vicious, self-sustaining feedback loop. The extreme ambient heat of the region ensures that the amount of water vapor available to condense is unprecedented. The stalled front acts as the trigger, constantly pulling the trigger on a thermodynamic weapon that wrings out this bloated atmosphere like a sponge. The result is precipitation efficiency that defies historical modeling. The rain is not just falling, it is effectively being compressed out of the sky by a thermodynamic engine running on pure, unadulterated heat. The ground, already defeated by the freight train effect, now faces rainfall rates that physically exceed the terminal velocity of standard urban drainage geometry. The scientific reality of this threat is reflected in the urgent, highly elevated alerts being issued by the Weather Prediction Center, WPC. For meteorological analysts, the excessive rainfall outlooks issued by the WPC are the ultimate arbiter of flash flood probability. Currently, the WPC has painted stark, undeniable bullseyes across the Gulf Coast. We are looking at sustained moderate and high-risk categorizations for excessive rainfall. To provide scientific context, on an annualized basis, high-risk days account for only a tiny fraction of the WPC's total forecast, typically less than 5%. Yet, these rare high-risk days historically account for over 80% of all flash flood-related fatalities and nearly 90% of all structural flood damages in the United States. A high-risk issuance is not a suggestion of poor weather. It is a federal declaration of impending infrastructure failure. The geography locked in the crosshairs through the duration of this weekend is uniquely vulnerable. The target zone stretches brutally across the Florida Panhandle, arcs through the coastal plains and river basins of southern Alabama, and deep into southern and central Georgia. This specific topographical layout is highly problematic. The terrain here transitions from flat, low-lying coastal estuaries to subtle inland elevations. When the deep southerly flow of moisture off the Gulf of Mexico is continuously shoved inland, it encounters this slight elevation and the friction of the landmass. This creates subtle orographic lift and coastal convergence, additional localized forcing mechanisms that exacerbate the heavy rainfall. Furthermore, the hydrology of this region is governed by major river basins: the Apalachicola, the Choctawhatchee, the Chattahoochee, and the Flint. These are massive dendritic drainage networks. As the localized urban storm drains fail, as the concrete bathtubs overflow, millions of acre-feet of runoff are forcibly routed into these river channels. The soil moisture profile across these states is already peaking. The ground is completely saturated, meaning the flash flood guidance, the amount of rain required in a short period to initiate immediate flooding, has plummeted to less than 1 inch per hour in some counties. With the stuck conveyor belt delivering 3 to 4 inches per hour, the rivers have nowhere to go but out of their banks. Despite the dire warnings, the WPC outlooks, and the collapsing infrastructure, there remains a dangerous, pervasive complacency embedded in the local coastal culture. It is a psychological defense mechanism born of routine. The most common phrase heard in the days leading up to an event like this is, "It's just afternoon summer thunderstorms. We get these every year. It will rain for an hour, the sun will come out, and it will drain." As a meteorological analyst, it is imperative to decisively dismantle this myth. Relying on this logic right now is mathematically and atmospherically fatal. The typical summer storms the public is accustomed to are known as air mass, or diurnal thunderstorms. They are triggered strictly by the daytime heating of the Earth's surface. They pop up at 3 p.m. as the ground bakes, they dump rain, and by 5 p.m., they undergo a natural death. A typical diurnal thunderstorm is the architect of its own demise. As the rain falls, it pulls down a column of cold air, the downdraft. Because there is no strong upper-level wind to tilt the storm, this cold downdraft crashes directly onto the surface and undercuts the warm-up draft, effectively choking off the storm's own fuel supply. The storm suffocates itself. What is happening right now is a completely different mechanism. These are not pop-up air mass thunderstorms. These storms are anchored to a synoptic scale stationary boundary. The stationary boundary acts as a permanent wall, separating the cold downdrafts from the warm-up drafts. The storms do not choke themselves out because the boundary continuously forces new, boiling Gulf moisture up and over the cold pools left by previous storms. They are feeding off a continuous, synoptically driven pipeline of moisture, independent of daytime heating. They will not die when the sun goes down. They will not dissipate just because the local temperature drops a few degrees. They will continue to violently regenerate at 2 a.m. in the pitch black, exploiting the stationary front, feeding off the heat moisture battery of the Gulf, and burying sleeping municipalities under catastrophic volumes of water. Treating a boundary-driven training complex like a standard summer shower is a fundamental failure to understand the lethal physics of the atmosphere. The sobering reality of the extended forecast is that this atmospheric roadblock is locked in place through the entirety of the weekend. The upper-level pattern is stagnant, the front is entirely immobilized, and the conveyor belt remains stuck. For the populations trapped under this stalled boundary, the danger does not end when the rain pauses for a few hours. The hydrology of urban and riverine flooding operates on a severe time delay. Even if the radar temporarily clears, the millions of gallons of water dumped 50 miles upstream are currently navigating the swollen river basins, rushing toward the coast. A river may not reach its peak crest until 48 to 72 hours after the heaviest rain has ceased. This time delay is exactly why attempting to navigate flooded infrastructure is so lethal. When a motorist encounters water flowing across a roadway during a break in the rain, the assumption is often that the water is receding. In reality, the hydrograph may still be climbing. The water is actively rising, and the next cell of the training complex is already spinning up just over the horizon, preparing to add a new surge of hydrostatic pressure to the grid. It only takes 12 inches of flowing water to exert enough lateral hydrodynamic force to sweep a 3,000-pound vehicle off an asphalt crown and into a submerged drainage ditch. We must redefine how we perceive severe weather threats. The general public has been conditioned to measure the severity of a meteorological disaster by the presence of a name. We wait for the National Hurricane Center to assign a designated moniker, a Hurricane Ian, a Hurricane Katrina, or Hurricane Harvey, before we mentally authorize a state of emergency, but the atmosphere does not care about our nomenclature. The physics of water do not require a central eye, a closed low-pressure circulation, or a named designation to dismantle a city. The sheer volume of water currently being extracted from the Gulf of Mexico and hurled against the concrete infrastructure of the southeast is easily producing hurricane-level destruction. The hydrostatic pressure rupturing the subterranean pipes, the Archimedean forces floating vehicles out of their driveways, the thermodynamic battery fueling the relentless training cells. These forces operate entirely independent of a category on a scale. There is no hurricane on the map, but the threat is absolute. The freight train is on the tracks, the conveyor belt is stuck, and the water is rising. If you reside in the WPC's high or moderate risk zones, you must disregard the tranquil tropical outlooks and treat this stalled boundary with the exact same reverence and defensive posture you would afford a landfalling cyclone. Heed all local flash flood warnings immediately. Do not attempt to calculate the depth of moving water over a roadway, and above all, understand that in a stagnant atmospheric environment, the absence of a named storm is merely an illusion of safety. Stay vigilant, stay off the flooded roadways, and subscribe for the latest analytical updates as we continue to track this historic meteorological gridlock.